Welcome to Code Breaking 2, Easy to Moderate. In a previous video I commented on the realism of Mr. Robot in code breaking. One of the characters of the show used it as an introduction. Because nothing says, "Hi, I'm playful and fun," or "we should get to know each other," than a message that could take hours of mathematics and coding to read. About me. I'm a security analyst with over 10 years of experience in the computer industry. I started in networking, moved to administration, programming, and then finally security. I'm an MCP and I hold a total of 8 standard certifications including networking, administration, and security. I have over 30 smaller certifications and endorsements. But what I really like to do is mess with computers, security, play video games, guitar, and when I have a job and can afford to, I like to go dancing and go to the gym. The intended audience. The intended audience is security researchers, red or blue team, programmers implementing encryption algorithms, technical staff that want something to show executives or project managers so they can understand what's at stake, and mathematicians. The goal. The goal of this video is to introduce the basics of statistical code breaking, to promote the use of properly implemented encryption, to aid in the explanation of the need for the proper time and consideration for encryption to leadership, and maybe to promote myself a little bit. But first, the math and theory.
The hikers were last seen 174 hours ago. Since then, 3 very big storms have hit here. There's a 1.24% chance that all of the hikers are alive. There's a 3.87% chance that one or more of the hikers are alive. I talked to a man. Watch that video now.
Gotta love the Onion News Network. The scenario. We don't know the key length and we don't know the key. We don't necessarily need the key length, as we can increment a key length counter and increase the key length to discover the key, or assume that the key is one of several typical key lengths and just try all of those key lengths. We know the encryption method. It shifts characters in either direction by either adding or minusing the value of the key. If it goes over 255, it wraps or truncates the value by subtracting 255 from it. We know the original text is in English for this example. So there's 2 methods: a combination of elegant force and frequency analysis, or raw frequency analysis. There's probably other methods, but those are the 2 that come to my mind right off the bat. The first method relies on the frequency of characters to determine the key by statistics. The second method is raw math. Knowing the frequency of the characters and a language and the key length, you can decode the message. English has 26 lowercase characters, 26 uppercase characters, 10 numeric, and around 34 symbols. Computers store characters as numbers. The process of converting this to text is called encoding. ASCII and UTF are examples of this encoding. ASCII and UTF share a numbering scheme to a point. 0 to 255 for the sake of this discussion. Given enough text, if we sample the text and average the ordinals, the numbers that they're stored as, of that text, it should eventually average out to the average of the text range. In this case, since a majority of our numbers are going to be lowercase, it'll end up being around 100 to 109. So all languages have patterns, and patterns of spaces and symbols that make them more readable to a greater or lesser degree. In the English language, we use space a significant amount of time. Of the 101,232,753 characters sampled, 18,496,842 of those were space, or about 18.27%. Of 33,251,000 1,884 words across a number of text samples, the word "the" appears 3,497,460, or about 10% of the time. Given this, we have a distinct pattern we can search for. Given a pattern, we should be able to discern or derive the key using averages. If we sample enough text, the clear text under the cipher text will end up averaging out for the most part. If we can get an average on each position of the key array, we should be able to determine the average. Armed with the average, if we remove that from the equation, we should be able to derive the key. So O is the original value and C is the key value. So our cipher is basically O equals O plus C. If O is greater than 255, we subtract 255 from it, so it's between the range of 0 and 255. The key that we're going to use is going to keep the text within the ASCII range, which means that the characters are probably going to fall below 128. This just makes it easier to understand how it works. It doesn't necessarily have to be that way. It just makes the algorithm a little bit more complicated in the flow. The key will be 256 bits long, or 32 bytes. But the length is fairly arbitrary, since we will not be trying to calculate the entire key. By that I mean we're not rolling through the key each 8-byte segment at a time and incrementing it and then trying the key. We're deriving the key based on statistics. We will assume a length of 256, but we could start at 0 and iterate to 256, or 0 to 32 in the case of 8-byte chunks. We're going to take a chunk size that is the same size of the key. Then we need to break up the text into 256-bit chunks, or 32-byte long chunks. And then we store the average of those 32-byte chunks in an array that's 32 bytes long. The average of all of those numbers is on the high side, since all of the underlying text should average out. If we can figure out that number, we can subtract it from the key values and derive the key. We know it should average to be around 109. But text with a lot of numbers or capitals will cause it to shift lower. There are a number of ways that we can get our first guess. We can loop through and just start subtracting until we find the average for the text, or we can take the number from the average and half it. Given that A starts at 65, we could start there. The average of 256 of a 256 block is that 256 block is our key. If you'd like to try this challenge on your own, this is a good place to stop the video. All right, on to the code. It's basically the target audience. This part's going to be a little tedious. I apologize for that, but this is so that we can cover the needs of all of the target audience. Looking at the code, our first function is the encrypt function, which is right here. And this basically just does the character shifting that we were talking about. So it does the addition. The second function is the decrypt function. And given the key, it could decrypt it. We're not going to have the key, but we're going to need this to try and test the key. So then we have the head function. This just returns an X lines of text. And we have the char head. The next function we have is char head, and char head gives us the X number of characters from the beginning of a file. We can't read an encrypted file line by line because the spaces and the line feeds are encrypted. The next function we have is the character count, and this basically is what we use to validate the results. So with the knowledge that space occupies about 18% of the characters in a given text, which is going to fluctuate depending on how many the text sample basically, but it's going to be over a certain amount and there's going to be a margin of error. So as we look at it, we need a way to determine how many of the characters are a certain type of character, and that's what this function does. Then finally, we have the find key. And what find key does is splits the files into 32 byte or 256 bit chunks, and then takes the 32 byte array and averages it across all of those chunks. In this part of the code, what we're doing is handing the key in and telling it to go ahead and decrypt it with the original key, which I have up here. And then we're going to get the characters, the beginning of each of the files, to show that they're encrypted. Then we're going to create a list of all of our crypto files, and we're going to read those in to our find key. So basically it's going to split those up and get an average of all of the 32 byte array. Then it's going to try and determine the number that we need to subtract from each of those byte array positions, and it's going to basically get our first guess for the key. And so it's going to give us our guess, and then it's going to compare, or it's going to show the comparison of the original key versus the guess key. And then we're going to blank the key out to show that the memory region for the key is not being used in the decrypt function. So in case it was using the same text, it's not pulling the key in into the function call. And then finally we're going to print the results with the drum roll. So with all that, go ahead and run this. And while it's running, you can see that it's given us the encrypted text, or the cipher text, here for 2 of the files, like we had specified in our code here. And then it gives us the best rough guess after it runs through all of that. So our best rough guess is here, and you can see that the original key doesn't differ much from our best guess key. The conclusion: by developing our algorithm and coding one of 2 methods to break the product cipher, we can successfully demonstrate that there are a number of additional security measures that we lack in this algorithm. We demonstrate how statistics can reduce the number of guesses in the weaker forms of encryption. We can also demonstrate how language frequency analysis can be applied to cryptography. We can also infer that anything that produces the same output cipher each time the same text is supplied, i.e. if we supply the text, it will always produce SKF 3 pound 4F, for example. It has a chance of being broken. We also know that breaking a weak implementation of cryptography is trivial enough to be performed by a wristwatch. The statistical part isn't limited to English, as it is the average of a range of characters used. The statistical part isn't limited to English, as it is the average of a range of characters used. This highlights a few best practices. While it may not seem like it, there's been considerable time and effort put into this video, years of studying computer security, research into encryption, coming up with demonstrations that illustrate the concepts, and the time it takes to make this video. I'm not employed. Security videos aren't all that popular, at least that I've seen, so YouTube pays poorly for security videos. And I don't have a cat to make cat videos of, so donations are appreciated. So like Julius Caesar, you get to vote whether I'm worthy of living by giving me a thumbs up, or have YouTube finish me off by giving me a thumbs down. So click subscribe, or you can donate on my Patreon. The details will be below. Thank you, and thanks for watching this video.